about that water is the universal solvent. And I made that statement about how I like to soak pots and how water has that ability to kind of allow things to dissolve into it. And one of the things you want to understand is, what does this term or word dissolve mean? And so when we're talking about something dissolving, we're talking about kind of like what you see with salt or sugar, for example. When you add that material to a solution, the actual physical appearance of it will kind of disappear, but some of the molecules will spread themselves throughout that solution. So when we talk about something dissolving in a solution, and especially this concept that we're going to be discussing, I just got done reviewing it with my 211 section about certain properties of certain chemicals. Just kind of build that foundation. Pay attention today, which I know you all are doing, right? But when we're discussing substances that do not dissolve, right? One of the things that looks awful. One of the things that we will see is that they have one of these characteristics, like they're nonpolar, right? And so what it means when something's nonpolar, usually there's, you know, how a magnet has a north pole and a south pole, and how we talked about how certain molecules can have a positive end to it and a negative end. All right, those are going to be polar structures. All right, nonpolar means there's really no charge in what we're discussing. So nonpolar substances will not dissolve in water. Okay, so we refer to those as hydrophobic, water-fearing. You know what else is water-fearing or hydrophobic? A rabid dog, or any animal with rabies, so something, I know I just threw that out there, but something to remember. So one of the ways I think about when something's hydrophobic, it's foaming at the mouth. That's just how I try to learn things. So now, what substances do dissolve in water? Right, and you'll notice the first two things that are listed up there are polar molecules and ions. And we're all familiar with what an ion is, right? What's an ion? Don't be afraid, just shout it out. Right. It's a molecule, all right, that's lost or gained an electron, which means it either has a positive or negative charge. All right, and that's the simple, if you want the simple definition of an ion, a charged particle. Okay, and it's charged because it's either gained or lost an electron there. And so these molecules will dissolve in water, and so we refer to them as hydrophilic, water-loving. So when you add this substance to a beaker of water, it will dissolve away. And so that's what we're looking at. And that's essentially what you see with salt. When you add salt to water, right, it dissolves into the water, and the sodium and chloride ions, all right, will break apart, right? And so they'll dissolve into the water. So keep that in mind when we're talking about, and I'll get to my point on what we're going to be discussing, because this brings us to the next part, because we're going to start talking about acids and bases here, and folks aren't too crazy about those subjects, but I'm going to give you just the basic understanding. So when we're talking about water, first of all, that statement at the top of that slide says it's a neutral solvent, right? And so when we talk about a neutral solvent, we're going to be discussing the property of water when we're relating it to acids and bases. So essentially, water won't be acidic or it won't be basic. It'll be neutral, right in the middle, like Switzerland there. And so what we're going to talk about is water on its own will randomly and spontaneously dissociate, which means that H2O, that molecular formula, it will just kind of come apart, right? And this happens randomly, and it happens really spontaneously. So the number up there that you see is 1/10 millionth of an ions per liter. So it doesn't, you don't see it too frequently, right? But that's essentially what we're looking at here. And so when water disassociates, right? I better write it down. When water disassociates, according to the equations here, you have H2O, and then you have another H2O molecule. And what you'll see is, this is what we're looking at up here, right? So when water disassociates, it spontaneously breaks apart, what we'll see is it's going to result in one hydroxide molecule and one what we call proton or hydrogen ion. Okay, you can see the little plus sign there. Okay, so these are both going to be polar molecules. So water, when it spontaneously just breaks apart, it'll give us a negative something and a positive something. And so when you have one negative something and one positive something, what do those charges do to one another? You know, they'll cancel each other out. So therefore, water remains neutral. Y'all see that? The water breaks apart. One positive ion, one negative ion, they both cancel each other out. Therefore, water is neutral. Right? So this just happens spontaneously. And sometimes that hydrogen ion right here will go to another water molecule and it'll form what we call a hydronium ion. Am I going to test you on that? No, but I just want you to know what we're seeing here. So keep that in mind. That's what we'll see in some instances. But the point being is that really what I want you to focus on is this part right down here. When water spontaneously dissociates and breaks down, you get a positive substance or positive atom, which is the hydrogen, and then you get a negative atom, which is the hydroxide. Hydroxide is here. Hydroxide ion is H or OH negative. Okay, so why am I telling you this? Because I'm leading you into this topic here, acids and bases. So this is something that's going to, I don't want to say plague you, but revisit you from time to time through this class and when you get into the physiology of some of your other systems in the body. For example, when we're talking about acid-base balance in your blood or pH balance in your body or even in your digestive system. But more on that, all right, in later chapters. But what we're going to see here is that an acid, and you want to know this definition here, an acid, when you add it to water, when it breaks apart or dissociates, will give you one of these, a hydrogen ion, an H+, and an anion. What the heck is an anion? What do you remember from last class? It's a negative ion. Right, exactly. Right, so that's what's going to happen. So the famous acid that we always talk about is going to be this acid in your stomach, hydrochloric acid, HCl. And so when hydrochloric acid gets dissociates into water, it gives us, of course, our hydrogen ion, and then the anion is going to be our chloride molecule right there. So that's what it's going to look like. But keep in mind, all right, we'll discuss it, but an acid is always going to form that relationship. It's going to have the hydrogen ion and then an anion, a negatively charged ion. So another name for that hydrogen ion right there is called a proton. So if you didn't have enough to worry about in trying to learn all this new information, we learned last class that a proton was a subatomic particle that lived inside the nucleus of an atom. And you're absolutely right. That's what a proton is when we're dealing with the subatomic particles. But unfortunately, someone decided to also call, all right, the hydrogen ion, H+, a proton. So one of the terms that you can use to describe an acid is it's a proton donor. That means when you add it to a solution, water, right, it's going to break down and it's going to give off hydrogen ions or protons there. So if you're adding a lot of acid to a water beaker, what you're going to essentially do is those molecules will break apart and we'll start to see a huge increase in these free-floating hydrogen ions. And I'll show you a picture here to kind of explain it a little bit more. For right now, just kind of memorize that. So we add the hydrochloric acid to the beaker, and those molecules just start breaking apart. And so you're going to see an increase, a lot of hydrogen ions in there and a lot of chloride ions floating around in this beaker. And so stronger acids, we are going to see a lot of this phenomena happen. Weaker acids, not so much, which that helps us when we're dealing with what we call buffering, which I'll talk to here shortly. Okay, but carbonic acid is one of the weak acids that float around in our bloodstream and act as a buffer. And that means that they control the shift of your acidity of your blood, or the alkalinity, basically what we call the pH of your blood. We'll talk about what all that means. All right. So what's a base? Well, a base is going to be an acceptor. All right. So our base, when we talk about this concept here, that a base accepts the hydrogen ions when it's added to a solution. So that's what I think of when I talk about what bases are. Think of a sponge. Like a sponge absorbs water, okay? But bases are going to absorb or accept those free floating hydrogen ions that are in a solution. So in the previous example, I said we added hydrochloric acid to a beaker of water, and as soon as that hydrochloric acid went into the beaker, it started breaking apart. Well, when we add a base to that same beaker, that base is going to go around like Pac-Man and kind of gobble up those free-floating hydrogen ions that just came from the hydrochloric acid. All right, so essentially, we call a base a proton acceptor. And so a base is going to go around and it's going to suck up all those free-floating hydrogen ions that we just released previously from the hydrochloric acid, or from whatever that you added there. So just think of a base as a proton acceptor, and it's going to want to kind of attach itself, right, or gobble up those hydrogen ions there. So our stronger bases, we're going to see more hydrogen ion absorption. Okay, ammonia and bleach. That's why they're such good cleaning agents. And then our weaker bases will see less absorption. So the weaker bases are kind of like a wimpier sponge for the hydrogen ions there. Right, so you really just kind of, for right now, if you're not really quite sure, and I'm throwing some information here at you that you may not have seen before, for right now, just kind of memorize that. An acid breaks apart when you add it to a solution, and then a base is actually going to go in there and kind of gobble things up or collect hydrogen ions there. And so I'll explain why do you have to know this stuff. So quick question. What type of substance releases hydrogen ions when added to water? You have two choices. What do you think it is? We add it to water, and then all of a sudden, it's starting to release tons of hydrogen, free-floating hydrogen ions. What are we looking at? Yeah, exactly right. You're talking about an acid. An acid is going to dissociate and give us tons of, all right, hydrogen ions. So this slide here is a very important slide because it talks about a few important concepts here. So the first concept that it discusses is this, pH. Some of you may have heard of it. I hear it all the time on skin commercials and shampoo commercials. I always talk about it helps with the pH. And that's usually meaningless to me as a consumer. I don't know what that means, all right? As long as it makes my hair smell nice and feel good, that's what I'm concerned about. All right, but when we're talking about pH here in this class, pH refers to the amount of hydrogen ions, right, when we are measuring a solution, right? So keep that in mind. It's the relative amount of the hydrogen ions in a solution. So this pH, this unit, this way to measure, right, a solution in regards to acidity or alkalinity, right, we range it on a scale of 0 to 14. 0 to 14. So right in the middle of that scale is the number 7. And at the beginning of class tonight, I told you that, all right, that water is a neutral solvent. It's neutral. So that means in our scale, you've got 0 on one end and you've got 14 on the other. And right in the middle is 7. And so that means that neutral is in the middle. So that means at one end of our scale, right, we're going to see acidity, and on the other side of the scale, we'll see alkalinity or something that's basic. And I'll talk more about that. And so the reason why water has a value of 7, because remember, when you add it to it, when water spontaneously dissociates, it's going to give you a positive molecule and a negative molecule. All right, just memorize that part. So one of the things we're going to find, and this is an important concept, and I'll explain it to you in a second, pH and the hydrogen ion concentration are inversely related. So what does that mean? If something's inverse to something else, what does that mean? Anyone know? Anyone hazard a guess? Exactly. It's not that it can't go together. It's opposite. If one increases, the other one has to decrease. All right. So that's what we talk about with inverse relationship, and vice versa. If something decreases, the other increases. Right. So that's what we're referring to here. So for example, if we're going to increase our hydrogen ion concentration, that means the pH value has to decrease. And vice versa. If we're going to increase our hydrogen, or excuse me, if we're going to decrease our hydrogen ion concentration, that means our pH increases. So going back to our scale here, right? Anything to the left of this 7, that's going to be acidic. And then anything to the right of the 7, that'll be, I'm just going to put a B here, is basic. Guess it didn't matter. All right, so anything to the right of neutral is acidic. That means it's going to have a low pH on our scale here that I drew. Okay, so if you have a pH of 6, 5, 4, 3, 2, 1, you're acidic. If you have a value of 6.7, you're still acidic. A value of 6.9, you're still acidic. Right? If you're 7, you're neutral. But if you're 7.1, 7.2, 8, 9, 10, 11, 12, 13, 14, 15, no, not 15. All right, then you're basic or alkaline. All right, so keep that in mind. If we increase our hydrogen ion concentration, I'll repeat myself one more time. If you increase the hydrogen ion concentration, you're going to decrease the pH. So you'll be acidic. And vice versa. So basically, this slide tells you, right, when something is neutral, that means we're going to get equal parts. And water fits that bill. When water disassociates, you get one positive hydrogen ion or proton, and you get one negative hydroxide ion. One's positive, one's negative. They cancel each other out. So solutions, when you get a lot of this and not a lot of this, right, you are going to have an acidic solution, and therefore your pH will be less than 7. And then when you have solutions that give you a lot of hydroxide ions and not a lot of hydrogen ions or protons, that solution is going to be basic or alkaline, and we'll see that pH have a value of greater than 7. 8, 9, 10, 11, 12, 13. So for right now, just memorize that. I could go into the reasoning why, but I'm going to be honest with you, it's going to take up too much time, and that's more of a chemistry question. We're not dealing with that. I want to get onto the bio stuff. All right, so for right now, just memorize. So I'm going to shout out a number, and then you tell me if it is acidic or if it's basic. 12. All right. 2.
Acidic.
5.
Acidic.
Good. 11.
Acidic.
Good. Good. Okay. So high pH, you're basic. Low pH, you're acidic. Cool. 7 is
Neutral.
neutral. Perfect. Okay. Good. So this picture here is great because it shows, all right, here is a neutral solution. If you were to go through and count all of those little bubbles in there, all right, that have these letters in them, you should have equal amounts of hydrogen ions compared to the hydroxide ions. All right, so say you have 10 H's, you should also have 10 OH's because they're equal. But now when we look here, we're looking at our pH scale. Okay, so 0 to 14. The lower numbers are here at the top, and the higher numbers are here at the bottom. If you look here at these beakers with the solution here in it and our dissociated substance that we put in there, if you count all these up, you'll notice there's a lot more H pluses, hydrogen ions, than there are hydroxide ions, the OH negatives. Go through and count, feel free, right? But when we look down here at this lower beaker, we'll notice the opposite. A lot more hydroxide ions, the OH negatives, compared to the hydrogen ions or the protons, the H positives there. And so we have few hydrogen ions, which goes back to this, right? As our hydrogen ion concentration decreases, the pH increases, and that makes that value, all right, that pH value higher. So that's what we're seeing here. We don't have a lot of hydrogen ions in here. Now we go up here, we have lots of hydrogen ions in here. And so increase in hydrogen ion concentration, we're going to see a decrease in our pH. That's true. Lower pH, a lot more hydrogen ions floating around in there. So that solution is going to be acidic. And we go down to here, you look at this solution, fewer hydrogen ions, way more hydroxide ions. We're going to see a basic, all right, value to that. All right, this is just a brief introduction into acids and bases. Really, the reason why we bring it up is because I want to get to this concept here, neutralization and the actions of buffers here. Right, these are two important concepts. So when you look at, what do you do when you neutralize somebody? Somebody's attacking you and they say the assaulter was neutralized. What do they mean by that? Stops, yeah, all right. So when we're looking here at neutralization, we have a basic or acidic solution. All right, so going back to this page here, we have either this solution or this solution. And when we neutralize that solution, that means we want to get this basic or acidic solution back to the value of 7. So how do we do that? In order to neutralize, it's real simple. In order to neutralize an acidic solution, add a base. Okay? And in order to neutralize a basic or alkaline solution, add an acid. Cool? Simple. You do it all the time when you have an upset stomach and they tell you to take Tums, right? Because that's what Tums will do. It'll neutralize your stomach acid. You have an overproduction of stomach acid. And if you look here, I'm going to go right back to the slide. If you look here, here's your stomach acid pH. That's pretty low. Right? It's close to almost 1, but it's between 2 to 3. So that means we've got to add something basic here to get that value back to, all right, neutral, back to 7. And that's essentially what we're looking at. So when you hear me talk about neutralizing, right, a solution, neutralizing an acid, add a base. Neutralizing a solution that's acidic, add an acid. All right, so the other concept I want you to understand is buffering. Now, we'll talk more about buffering, especially when we get into when you take 211, and you learn about pH balance in the blood. Right? But when we're talking about buffering, notice, this is a big word here, it helps to prevent changes. So if you want to consider it a situation that a solution becomes acidic or basic as a problem, then we want to prevent it from becoming a problem. We want to prevent a solution from becoming acidic or basic. So to do that, all right, so, and we'll see it in situations physiologically, right? If we increase our carbon dioxide levels in our blood, we run the risk, all right, of our blood pH decreasing and becoming acidic. And we'll learn about that at a later date, right? But point being is, we start to see this problem starting to develop for whatever reason. Maybe your breathing rate, your respiration rate is decreased significantly. You're not able to exchange gases, all right, when you're breathing. And so your carbon dioxide levels increase inside of your blood and inside of your tissues. That's a problem. It's bad, right? So now our pH starts to drop. So before it gets to the point, right, where it we get to the point of no return, we want to prevent this from becoming a problem. Right? And so what we'll see with buffers is that when the pH starts to slightly change, for example, the pH value of your blood is this range right here. You want to memorize that. I just talked about that with my 211 class last night. The value of the pH for your blood is 7.4. Right? But the range is 7.35 to 7.45. So you notice that your blood is slightly basic or alkaline. Right? So now you start to increase the carbon dioxide level in your blood. And your blood starts to go from 7.4, 7.2, now to 7, now to 6.8. That's a problem because now you're starting to swing to the acidic level. And when your blood becomes too acidic, right, there's lots of different symptoms that start to develop. But one of the big things that can occur is what we call protein denaturation. And your proteins start to unravel. And when they start to unravel, they start to lose function. And a non-functioning protein is useless to all of us, all right? So we want to prevent that from being a problem. So we have these buffers, and you'll see two of them up here. I mentioned the carbonic acid earlier. That was a weak acid. And then there's bicarbonate, which is also a weak base. So if your blood starts to become too acidic, your bicarbonate levels, which is a weak base, start to increase to try to prevent that pH change and keep it at that normal 7.4. So if it starts to go to 7.2, the buffers start to interact, right, with whatever is causing that, whatever acid is causing that change in pH, and it tries to prevent it from changing the pH. Almost kind of like a neutralization on a, I hate to use that term because neutralization is a totally different term, but it helps to prevent the problem before it develops there. And again, it's hard for me to really explain this to you without going into the concepts there, but again, you will learn that at a later date there. So what is the general relationship of hydrogen ion and pH? What did we say? If you increase the amount of hydrogen ions in a solution, what does that do to the pH of that solution? Right. It's that inverse relationship, right? So that's what we're going to see here. Greater hydrogen ion concentration, lower pH, because it starts to go down. And vice versa. Right? So if we have a lesser or few hydrogen ions in a solution, then our pH goes up. Okay, inverse relationship. This is the first time because there's going to be lots of inverse relationships that you're going to learn in this course, and this is one of them. Okay, good. Let's get past that stuff. I want to get, not that that's not cool stuff. I actually enjoy it, but I want to get into the biological macromolecules. Does anyone here count their macros? Does anyone know what that term means? Yeah. Most people, if they're on, if they're trying to regulate their, I hate to say diet, but their diet, you know, what they're going to be eating. Some people like to count their macros, meaning they're only allowed so many carbohydrates, so many fats, so many proteins, all right? And they'll base it on a unit of measurement, usually grams. So, but when they say macros, they're referring to macromolecules. They're referring to these organic molecules that you see listed here on the bottom of your screen. Fats, lipids, carbohydrates, sugars, right? Nucleic acids, think of DNA, RNA, and then proteins. So that's what they're referring to. So when we're looking here at our molecules, you can have organic molecules and inorganic molecules. Simple definition. And for those of you that have taken organic chemistry, that should look familiar to you, right? What is considered an organic molecule? Anything that has carbon in it. Would you believe me when I tell you that plastic is considered an organic molecule? It is. Because why? Look at the definition up there. It contains carbon in its molecular formula. It is. I can't help that. I got into an argument with somebody about that one time and they did not believe me. And I said, look it up, Google it. I love it. I love that term, Google it. All right. So that's what we're looking at here, right? So any molecule that has a carbon in it is considered to be organic. Okay. Now notice this says most, not all, but most are going to be found in our living organisms here. All right. So then our inorganic molecules are all the other ones. So let's look at these 4 very important biomolecules, these macromolecules that are present in living organisms and systems there. Okay. So lipids, carbohydrates, nucleic acids, and proteins here. All right. So our biological macromolecules, what we're going to be talking about here in a moment, right, can be synthesized, utilized, produced, made in our bodies, but also broken down in our bodies. And so when we're looking at these organic molecules, we will see that they will have these 3 very important atoms or elements: carbon, hydrogen, and oxygen. And when we talk about the 4 major, right, molecules in your body or atoms, those are 3 out of the 4. In fact, those are the top 3 out of the 4. Nitrogen is the 4th one. All right. Now, some of these large organic molecules will occasionally have these elements that hang off of them or be attached to them. So we have what we call our carbon skeletons. And so our carbon skeletons are going to be this part of the molecule that has a bunch of carbon atoms attached to it. And if we're only dealing with a molecule that has hydrogen and carbons, all right, that make up that molecule, when the molecular formula only contains C's and H's, then we call those hydrocarbons. If there's an oxygen somewhere in that, then it's not a hydrocarbon. Okay, so it's only going to contain H's and C's, or carbon and hydrogen. So you'll hear terms like functional groups, right? And functional groups, right, without going into a long definition, these will be, in most cases, multiple molecules that are attached onto our carbon backbone or the carbon skeleton that are going to confer certain physiological, chemical properties, physical and chemical properties, right, to a molecule. And so these functional groups can be apolar. Right, so that means now if we've made a molecule polar, we've changed some of its properties. We've made it where it can dissolve in water, for example. Okay, because remember, non-polar molecules do not dissolve in water, but polar molecules do. By simply adding this functional group, we've now turned our molecule into something that can dissolve in water, which can be helpful when we're talking about certain substances. And then, since we just talked about acids and bases, when we add these functional groups onto some of these molecules, right, it can now turn, right, or make that molecule act like an acid or a base. And we'll discuss some of this later on. All right, let's talk about fats, lipids. All right, so lipids are going to be what we call, one of the properties that they have is water insolubility. What does that mean? If you've ever boiled water before, well, say you want to make some pasta, spaghetti. All right, now I was told, and I'm not a very good cook, but I was told that when you boil pasta, add a little bit of oil to it. Does anyone know why you add oil to the water? Exactly. Yeah, that's what I was told too. So the pasta doesn't stick. All right. So I do. I add a little bit on there, but you notice when you add it on there, it's floating on top. It doesn't dissolve away. You can always see it until the water really starts to boil. But that's because it cannot dissolve. So oils, which are going to be lipids or fats that are going to be in a liquid state at room temperature. That's essentially what an oil is. It's a fat, but it's in the liquid form at room temperature. So these molecules, these substances will not dissolve, all right? They are insoluble, or in this case, water insoluble. They will not dissolve in that water there. So next, I want you to know these important aspects of lipids is that, one, lipids are stored form of energy. Okay, an example of that would be triglycerides. Right? They also make up our cells, right? The cell membrane, which we haven't talked about yet, which we might have time to talk about it today. But a cell membrane is that outer part of the cell. Like an envelope is to a letter, the cell membrane is to a cell, right? So the cell membrane contains the other components of the cell. And so about half of that cell membrane is made up of lipids. Right? We also need lipids to make certain hormones. For example, estrogen in women and testosterone in men, right? Cholesterol, which is a form of fat, we need cholesterol. This is why cholesterol is not necessarily a bad thing. It's actually a pretty good thing to have. We need that cholesterol to help make certain hormones, like, for example, our steroid hormones, estrogen, progesterone, and testosterone. So the 4 classes are listed here below, right? So you have triglycerides, phospholipids, steroids, and eicosanoids. And we're going to go through those. Okay, so triglycerides, phospholipids, steroids, and eicosanoids. Some of these terms you may have heard. Most people have heard of steroids, and a lot of folks have heard of triglycerides, especially when you go get your blood drawn and they do a lipid profile on you. And you come back and you look to see what your triglyceride levels, and then you look at your good cholesterol, which is the HDLs, and the bad cholesterols, which are the LDLs. All right, so we're going to talk about those. Let's start off with triglycerides. Okay, memorize this, know this. Triglycerides are the best, all right, form of stored energy. And we say long-term energy because you can use it. You can build up your adipose tissue, right? And that's essentially us saving, right, the triglycerides for a later time or a later date, whenever you're going to utilize them. Okay, say you're going to go on Survivor. And I've already thought about this because I wanted to go on Survivor a long time ago. And I said, if I went on Survivor, I would put on about 40 or 50 pounds of fat, because then I could get away with not eating for a long period. I would eat, but you know what I mean, right? So long-term storage, that's what your triglycerides are. So your triglycerides are made up of 1 glycerol molecule and 3 fatty acids. All right, you want to know that. So 1 glycerol molecule and 3 fatty acids. And so there's different type of fatty acids. We have different classifications. There's short chain fatty acids, medium chain fatty acids, and long chain fatty acids. And the names actually describe literally what the fatty acids are. If you're a short chain fatty acid, you're not too long, right? And a long chain fatty acid is really long in comparison to the other 2 types. There's just more carbons in a long chain fatty acid than there are in a short chain fatty acid, right? So when we're looking here at fatty acids, we're going to see that some fatty acids will have a double bond. Those are those covalent bonds that we're talking about, those shared electrons, right, between carbons. Because remember, we learned that carbon, all right, wants to form covalent bonds. It doesn't want to lose its electrons, all right? And it doesn't necessarily, it wants to gain electrons. And the only way for it to gain those electrons is to share it with another molecule. Okay, and so that's what we're going to see here. So when we see 2 pairs of shared electrons, then we have what we call a double bond. So when we talk about fatty acids that are saturated fatty acids, that means they do not have any double bonds. And then when we look at fatty acids that are unsaturated, they are going to have 1 double bond. And then obviously polyunsaturated, poly means many, okay? That is going to be 2 or more double bonds. Okay, another situation in which you have to just do a little bit of memorization. So if we're dealing with a saturated fat, that means there's no double bonds. If we're dealing with an unsaturated fat or a unsaturated fat, then that means we're going to be dealing with at least 1 or more double bonds, depending on which one we're talking about. All right. So a little bit more here on the triglycerides. One of the things you definitely want to know, this is one of the most common forms or types of lipids in the body here. And what I also like to talk about, in addition to energy, fatty lipids, triglycerides, all right, when they're in the adipose tissue, right? If you increase the adipose tissue, so the triglycerides there will increase cushioning, insulation, and actual what we call structural support. Now, when we learn more about some of the internal visceral organs, you'll understand a little bit more what I'm talking about. Right? But, for example, your kidneys, are surrounded by what we call perirenal fat, right? It's a coating, essentially a coating of fat around your kidneys. And so your kidneys, what do you think? The reason why we have that coating of fat around the kidneys is so when your kidneys are getting banged around, let's say you're in a really bumpy car or something that you're bouncing around. And so when your kidneys start to, impact against your ribs, because they sit right against your ribs here in your back, it's so they don't get damaged. So they're offering cushioning. I once went swimming with a friend of mine in, I think it was the month of November. It was really cold up in New York. And he's a much more larger man than me. Probably about 100 to 150 pounds heavier than me, but he's shorter than me. So he has a lot more adipose tissue. So we jumped in this lake up in the Adirondacks called the Blue Mountain Lake. Water is freezing. I lasted about 2 minutes maybe in that water. He lasted about 20 minutes in that water. And the reason why, he had more insulation than I did. Right? So that adipose tissue, the lipids in that tissue helped to insulate him, kept him warmer. All right. So when we're talking about the relationship between triglycerides and adipose tissue, the purpose of adipose tissue is to store the triglycerides for a later day. And so when we're making triglycerides, that process is called lipogenesis. Genesis is to create, to build, to make. Lipo means lipid. So when we put that together, lipogenesis, we are going to make these triglycerides and we're going to put them and store them into our adipose tissue. When do we do this? When you have a lot of nutrients available. When you're in what we call the fed state. Okay? When you're living here in the United States, right? You're going to be pretty much in a fed type of scenario, right? So if you're hungry, what do? You usually go to the refrigerator or out to the store or a restaurant to get some food. So you'll have an excess of nutrients. So our bodies like to store those nutrients. And that comes from a long period of adaptation. When we were nomadic people, hunter-gatherers, and our tribes moved around, we never knew when our next meal was going to come, right? Depending on what the food sources were like. So your body adapted over time. And so when you had excess nutrients, it would store it for a rainy day. And that's what our adipose tissue does. Now, when you go on Survivor, right, all that fat that you built up, okay, you now need it to do all the different challenges and when you're not getting a lot of food, right? So what we're going to start to see happen is our triglycerides are going to be broken down by our body. And we're going to release those triglycerides and we're going to start to chop them up into glycerol and those 3 fatty acids. Right? And the purpose of that, all right, is when we are not in the fed state and we need energy from those nutrients, those triglycerides. And so that process, when we start to release the triglycerides and chop them up, is called lipolysis. Lysis means to break apart. Lipo or lipo means fat, okay? So when we're breaking down fats, we're going to break down the triglycerides when we need energy from those fats. When we start to store and make triglycerides, we call that lipogenesis. And those occur in your adipose tissue. So this is a picture of what a triglyceride looks like. Those 3 red dots that you see on the top here, that's the glycerol backbone right here. And then you have these strings coming off, those black balls and I don't know, it looks like light blue balls that are attached to them. Those are your fatty acids. And you'll see here, right, here's a fat, this fatty acid is different from this fatty acid, which is different from this fatty acid. They don't all have to be the same type of fatty acid, right? They'll be varying lengths. You could have 2 short chain fatty acids with 1 long chain fatty acid. That's not important here, right? But just notice you'll have these 3 fatty acids here. So when we have a triglyceride molecule, which is this molecule right here, the glycerol backbone with the 3 fatty acids attached to it. So when we make this molecule, we call that lipogenesis. And then when we want to take this triglyceride molecule and break it apart so we can get energy from it, we're going to engage in lipolysis or lipolysis, and we're just going to break off these fatty acids, snap them off, and get rid of them off of the glycerol backbone here. All right, the next type of lipid is going to be our phospholipids. And our phospholipids, these are the most abundant type of lipid in your body. Why? Because they're in every single cell. Phospholipids make up, all right, a sizable portion of your plasma membrane. Right, so they play a huge role, all right, in the functioning, and we'll talk about that in chapter 4, but they play a huge role in the cell membrane there. So when we're looking at a phospholipid, you'll see this term called amphipathic. And that means, right, the one molecule has both a polar aspect to it and a non-polar aspect to it or component. Right, up until this point, I told you something's either going to be polar or non-polar. Well, there's always exceptions to the rule. I'll let you know when that is in this course, and this is one of those. All right, so phospholipids have both a polar component and a non-polar component. And so when you look at a phospholipid, right, initially, you'll say, oh, wow, it kind of resembles and looks similar to a triglyceride. Except, right, when we're looking at it, you're not going to have 3 fatty acids. You're only going to have 2. Right, and so when we're looking at our phospholipid here, you're going to see the glycerol portion of it will have a polar, what we call a phosphate group on there, because phosphate's a relatively large molecule there. And so it will have polarity to it. And then when we look at the other part of it, okay, we are going to see the fatty acid part that is going to have the non-polar aspect to it. So the polar aspect, which includes these structures here, the glycerol, the phosphate, and then any organic groups that are a part of that, those will be the polar portions. And so we refer to that as the hydrophilic head. I'll show you. I'm usually easier to draw. It's tough to draw with this mouse, but usually it looks like this. This is what a phospholipid looks like. And then you have 2 fatty acids that kind of come off. So the circular part here, that is going to be the head there. And so we refer to that as the hydrophilic or polar head. And then the fatty acids that come off, that's the nonpolar portion, and that's the hydrophobic or nonpolar tail to it. Okay, so remember, hydrophilic, water loving. It can reside in a water environment. It's happy there. It's fine. Hydrophobic, nonpolar, right? Water fearing. It does not want to be in a water environment. That's going to come back later on when we talk about the plasma membrane. So just kind of put some of that information in your head here. Okay, the third type of lipid is the steroids. There's that term again, hydrocarbon. So that means that these molecules are going to have hydrogen and carbon, all right, molecules in the molecular formula there. And it's an actual ring structure. Now, when we're talking about our steroids, one of the things that you're going to notice when we're discussing, all right, this classification of lipids here, you'll see one part of our lipids here is cholesterol. Won't get into that long, drawn-out conversation that I usually have, but cholesterol is good, especially in children. I'm not saying feed them, all right, fried chicken all the time or things that are really saturated in fat, right? But what I mean is we need cholesterol, 1, to make our steroid hormones, but 2, cholesterol is part of the plasma membrane. And we're going to actually see it. The more cholesterol that you have in a plasma membrane, the more resilient that plasma membrane is to changes in temperature. All right, so if you're in really hot or cold environments, that cholesterol helps to stabilize the plasma membrane so it doesn't get damaged. So that's one of the reasons why cholesterol is important. We also need it for our steroid synthesis to make testosterone and estrogen. Very, very important there. And then finally, when we talk about our steroids here, and we cannot not talk about bile salts. Bile salts are important in fat digestion. Your liver makes bile. Your gallbladder stores the bile. But bile, right, which contains the bile salts, is needed to mechanically break down your lipids, your fats that you take in from your diet. It's very important. So, of course, right, we need, right, lipids to help make those bile salts. Okay. Last part, eicosanoids. Try to learn as much as you can from this because you're going to revisit eicosanoids when you get into the endocrine system and you're learning about hormones. All right, so eicosanoids, also known as locally acting hormones, they come from this one specific fatty acid. It's called arachidonic acid, and it's in your plasma membrane. It's in every single cell's plasma membrane. So when there's damage done to the plasma membrane, arachidonic acid starts to go through these chemical reactions. We call it an enzymatic cascade, right? It's like stacking dominoes up and then pushing the first domino down, and it runs it in the next one, which knocks that down, which runs it in the next one, which knocks that down. All right. So arachidonic acid is going to be responsible for ultimately making these 4 classes of eicosanoids. And you may have heard of some of these, all right? Prostaglandins, prostacyclines, thromboxanes, and leukotrienes. These, all right, molecules here are going to be highly relevant when we're talking about the inflammatory response. So you're doing something, playing basketball, mowing your lawn, and you step on uneven ground or you step on another person's ankle while you're playing and you twist your ankle. What's one of the first things that happens to your ankle after you sprain it? Swells up. Yeah, swells up. Painful, but it swells up. That's this inflammatory response. And what caused that? The actual spraining or twisting your ankle. But guess what you did? When you sprained that ankle, you damaged the plasma membrane of all the cells in those tissues around your ankle. Not every single one, but a lot of them. And so that kicks off this process. This arachidonic acid starts to go through this chemical chain reaction. We call it the enzymatic cascade. And it ultimately is going to create these 4 classes. So there's certain drugs that you can take to prevent the formation of some of those classes during this enzymatic cascade, right? Have you ever heard of COX-1 and COX-2 inhibitors? It's a class, it's a class of drugs like aspirin, Celebrex, okay? Those are these drugs that block the formation of these enzymes that are found in this enzymatic cascade that will create these 4 classes. If we can never create some of these classes, we can decrease the amount of inflammation that occurs. What's one of the best anti-inflammatory drugs that you can give to somebody? What's usually the one when someone says, oh man, I hurt my knee and I got a blank injection into my knee? Steroids. Yep, steroids. Because guess what? Steroids, when you undergo this process, arachidonic acid will get broken down into another chemical substrate. You don't have to know this for this class, but steroids cuts that process off right here, right when it begins, which is really good. So it can actually prevent the formation of a lot of those 4 subclasses there, the prostacyclines, prostaglandins, theoretically. It doesn't always, because it depends on how much the extent of the damage there, right? But that's why steroids are highly effective, because they address the problem right away. right at that level of when the arachidonic acid starts to get broken down. Okay, so when we look here at this next slide here, and you heard me mention this briefly here when we were talking about oils, right? But when we're talking about fats in general, when we talk about our animal fats, most of the animal fats are saturated. So what does that mean? That means they lack a double bond. And so most animal fats, when they're at room temperature, will be solid in form. Perfect example, cook up some bacon, drain off the grease, leave it on your counter for a couple of days, or at least within 24 hours, and come back and look at it. It's solidified. It's become hard, all right? And so that's what we're going to see here with our animal fats. They will be solid at specifically room temperature. Now, when we talk about our vegetable fats, that's a different story. Those are going to be unsaturated, which means they have one double bond. And most of those at room temperature will be in the liquid form. Generally healthier, right? You don't hear your doctor saying go out and consume a lot of bacon grease. They usually say, have some olive oil or coconut oil, or if you're going to be cooking, right? Use those substances because they're generally healthier. Right? And so we can actually take some of these types of unsaturated fats and convert them, right, through the process of hydrogenation. You may have heard of this, right? And so hydrogenation is when we're going to convert these fats, right, from saturated to unsaturated. And what happens is from start to finish, as long as that process happens, not too bad. But sometimes we don't get to complete that process. So we've only partially hydrogenated something, and then we came across this awesome discovery of this group of fats called trans fats, which taste really good, but they're horrible for you. So much so that New York City has outlawed restaurants from cooking and using trans fats. I'm not sure if there's I'm sure there's probably some places out in California too, right? But they've outlawed trans fats. Restaurants cannot use them because they're bad, because trans fats, right, can increase plaquing in the arteries, increase your risk of heart attack and stroke. Has it been? Wow, I'm way out of touch. All right, that's good news. Really? All right, because I remember they made a bit when I first moved down here. Now, this was 13 years ago. They were talking about the time New York City was starting to ban it, and I didn't hear about it anywhere else. So it's fully banned in the United States. Perfect. Y'all should be happy about that, right? The federal government's looking out for your health, so it's working for us. All right, so when we're looking here at our lipids, there's different types of lipids that we'll be talking about through the course. One such group of lipids are what we call glycolipids. Glyco, think of carbohydrates like glycogen, right? And so what we've done is we have a lipid and we just attach a carbohydrate group to it. And you're going to see this, and we'll get into it more when we get into chapter 4, right? We'll see these glycolipids on your plasma membrane. Right, and so they'll help with determining, right, the identification of the cell surface there, which will come in when we talk about cell signaling there and binding. And then we have our fat-soluble vitamins, and we're missing one in this group here, all right? But your fat-soluble vitamins are A, E, and K. D is also considered to be a fat-soluble vitamin, and the reason why I didn't put it up there is because we're starting to classify vitamin D as a prohormone. Right? So vitamins are just enzymes, coenzymes, what we call them, right? You can still, for the purpose of this class, I'll still call vitamin D a fat-soluble vitamin. Fat-soluble vitamins are vitamins that if you take them in excess, they will be stored in your adipose tissue. And so you can start to accumulate, all right, your vitamin levels in that situation. Problem is, with fat-soluble vitamins, you can reach a limit that's starting to become toxic. Too much of anything can be bad. So if you get too much vitamin A, too much vitamin D, E, or K, especially with K, you can get blood clotting. You want to mess with that, right? So they're stored in your fat cells. Water soluble, no problem. because it dissolves in the water. And guess what you do with water-soluble vitamins when you consume them to excess? Pee them out. That's right. You pee them out, which is evidence. If you're taking a multivitamin, you go to the bathroom and your pee is bright yellow, you're peeing out vitamin B2, riboflavin. That's an expensive urine. All right. And that's because, right, your body's not, it's either not absorbing it, right, or it's absorbed enough and you're just paying for a lot of excess. So keep that in mind. Water soluble, no problem. All right, this is just a picture showing you our different types or different classes here of your lipids. Here's that picture. You already should know this one, the triglyceride. Here's our phospholipids. You're going to have your phosphate group, right, attached onto. All right, this is a great example of that phospholipid backbone here. All right, and then we have our fatty acids there. There's that polar head, and then this is this whole structure over here is going to be the polar head, and this over here is going to be the non-polar tail. And then here you can see our steroids, and you'll have your cholesterol molecule over here. These are the ring structures there. And then our eicosanoids down there. You're not responsible for knowing those structures, though, what they look like, I mean. All right, so which class of lipids forms the cell membranes? The most abundant type. Phospholipids. Yep, nailed it. Phospholipids. Okay, I'm going to stop here in chapter 2. I'm going to send out a video for you folks. Hold on one second. Because I want to stay on track here.